Hello everyone. I'm Ali Madani. I'm a machine learning researcher in Cyclica Incorporation. I'm going to talk about a concept that we've worked on recently in Cyclica, and it's about label confidence in deep learning settings. So what we like to have in deep learning or in general machine learning setting is large, high quality data. But that's not what happens in reality. So what happens in reality is having low quality or low quantity data. Okay, and the worst scenario is having both. So our data set is small and the quality is low. Unfortunately, that's not happening for us. But the question that happens, similar to many other aspects of machine learning, is the trade-off between choosing high quality and high quantity. Okay, and here let's define what we mean by confidence and quality. We are talking about label confidence, and it could be resulted from many sources. It could be confidence that we have because of expert annotation, for example, in radiological images or pathological images. We can have perfect or maybe a little bit different annotations of images. Okay, so that's fine. And we can have non-expert annotations. Okay, for non-expert annotations also we can have different levels of confidence. In both scenarios, that could have different applications. Expert annotation in radiological images, as I said, non-expert annotation in non-expert annotation in annotations of cats and dogs images. And so in all those settings, we care about confidence of the labels and data points in classification settings. The other two scenarios that happen for us or many other applications, specifically in medicine and biology, is about multiple measurements that we can have based on different technologies or repetition of the measurement of using same technology or even literature-based annotation. For example, we can have different papers reported that this drug interacts with that target. But the question is, so these are different reasons for having different levels of confidence. Why we care about it? Let's have a very, very simplified version of the problem. Imagine we have high quality and high quantity data. Two-dimensional space, we have two classes, class red and class blue. Data points in class red should be separated from class blue. We have a beautiful decision boundary, everything is awesome. But this is not what happens in reality. There are two other scenarios. One of them is high quality, but lower quantity. It doesn't mean that this data set is very small, but the quantity could be lower, resulting in lower coverage of space. When we have lower coverage of space, specifically in this region, it can result in the movement of decision boundary. Therefore, our classification may not be as generalizable as we want. And the other scenario that we care more in this problem, in this talk, is about low quality but high quantity data. And as we can see here, if you have high quality and high quantity and low quality data, the decision boundary also could be very close to the actual decision boundary, the decision boundary that we had to came up with. But we can have data points on the other side of the decision boundary in the other class because of experimental errors or so. And this is a very, very simplified version of the problem. It's not what's happening in reality. It's much more complicated. And why we care about the problem goes back to the technology we have in Cyclica Incorporation. We've developed Matchmaker as one of the technologies of Cyclica, and it's about predicting drugs and proteins, initially in human proteins in human genome. And what we have here is millions of data points as input of a deep learning technology, deep learning-based technology, to try to predict interaction of a new drug or ligand to target proteins. But we have different levels of confidence on data points. Okay. And we wanted to see, instead of choosing a threshold in the data set to just use high quality data as has been done before, could we use low quality but higher quantity part of the distribution, train the model, and further fine tune it in higher quality part of the distribution? But it reminds us of a specific concept in machine learning, which is called transfer learning. So in transfer learning, we have a ton of data in a reference task. It could be image classification in ImageNet, and we try to use that trained model and fine tune it further in a target task. For example, classification of images in radiological image dataset. And we wanted to implement a similar concept for across label confidence distribution. That was the reasoning behind filter transfer learning. So we came up with filter transfer learning technique in which we train a neural network model on lower confidence part of the distribution, which is just large part of the data set, and then fine tune it in higher quality part of the distribution. And we have evidence that if we do this training in the lower confidence part of the distribution in a stepwise manner, the performance gets even better. But speaking of performance, let's see if FTL results in better performance or not. And it does. So this is one of the results that we have in our manuscript. And what we see here is comparison of FTL results, which are the plots I showed here, compared to the dashed line, which is the best performance, either loss in the middle plot or accuracy in the right plot, for the neural network models trained only in one part of the confidence distribution. So the traditional way of learning in one part of the confidence distribution. As we can see, the loss is lower than non-FTL models, the loss of FTL, and the accuracy is better, is higher. But as we can see, we have a jump in performance in the epoch, at the epoch that we move from a step 1 to a step 2. Okay, and we wanted to investigate why it is happening. So for that, we care only about layer weights. Why? Because we're fixing all other hyperparameters of the model, all the hyperparameters of the model. And the only thing that is changing are parameters of the model, or layer weights of our fully connected neural network. So we compared the layer weights between FTL and non-FTL models, but we wanted to see how layer weights change across epochs. So here what we see is distance of layer weights between epoch 100 and 120 for non-FTL models shown in orange and FTL models shown in red. And why epoch 100? Because epoch 100 is when the model is converged for FTL and non-FTL models. Also, epoch 100 is the starting point of the second step of FTL. And as we can see here, the behavior of the first hidden layers are similar between FTL and non-FTL models. And by first hidden layers, I mean the layer weights of the layer weights connecting input layer and first hidden layer, and then first hidden layer and second hidden layer. So these layers behave similarly between FTL and non-FTL. But as we can see in the right part of the plot, the last layers change their behavior between FTL and non-FTL models. As we can see here, neural network slows down change in the layer weight, so the rate of change of layer weights from a step 1 to a step 2 compared to a non-FTL model. And that was helpful for us to understand what's going on in the neural networks that we are developing using FTL to be able to figure out how we can use it in our technology. Altogether, this suggests that FTL can be helpful to develop deep learning models across label confidence distribution to not get rid of low confidence part of the data, to use all the data that we have, and then do the stepwise process using FTL to get a better performance. But it is not only applicable to our problem in pharmaceutical industry for drug target interaction. We believe that it is possible to use it in many other applications, like radiological images, histopathological images. These are all maybe medicine or pharmaceutical related kind of problems. But there are many other problems in different industries dealing with this problem of label confidence. And at the end, if you're interested, you can check our manuscript, which is now in archive. If you search filter transfer learning archive, you can easily find our manuscript. And also, if there's an interest to check other technologies we've developed in Cyclica Incorporation, you can check our website. Thank you all for your attention, and I would be happy to answer any question you have.